Okay, so this is very similar to one we've just worked. Actually, the dimensions are, I think, the same, except it's not uniformly distributed load, it's a triangular distributed load. So let's apply the same strategy we have all along. We want the value at C, the internal forces at C, so I'll make a cut. So let's look at this side. The left side, what do I need for the left side to work? Well, I need reactions at A, and I have to resolve this triangular force. I think you can know the area of a triangle, right? Now about the right-hand side. Well, I only need one reaction, but look what I'm left with. It's a trapezoid. So just to kind of help you see it, I would have to figure out probably two forces. One for the rectangle, and then one for the triangle. So now it becomes a little more even. Which side you choose, I don't know. I think there's a little less work going to the left. So I'm going to go to the left this time. To go to the left, I need to find my reactions at A. So I'll draw a quick free body diagram of the structure. And I'll assume at A that AY is up and AX is to the right, and that my reaction at B is just vertical and also up. Now I need to get my concentrated equivalent force for the triangle. What's the area of a triangle? 1/2 base times height. So that looks like that's going to be 27 kips. And the centroid of a triangle is 1/3 the distance from the big end. So total dimension is 18. 1/3 of 18 is 6, right? So my load should be 27 kips, 6 feet from there, or 12 feet from A. So remember, I'm trying to find my stuff at A, so what do I do first? What's a good thing to start? That's a good idea. So I'm going to use right-hand rule for my sign convention for moments, and I'm going to sum the moments at B. When I do that, so about B, this 27 kip creates what kind of moment? Positive or negative? Positive. So the force is 27 kips, and the moment arm is 6 feet, positive. And AY is going to create what kind of moment? Negative. And that will be AY times this moment arm, which is 18. So it looks like AY is going to be 9. And just to be complete, this is a pretty simple one to do. If I do sum forces in the x direction and make sure I have equilibrium, the only force I have is AX. So it's 0. So now I'm going to cut the structure and use the free body diagram to the right. So there's my cut piece. It's 6 feet long. Let's put on my value for AY, which I found to be 9 and acting up. And then let's see what the applied load looks like. I know it's triangular. What's the intensity of the load there? Well, I know the intensity at the end is 3. If I want to know it here, you can use similar triangles. So 3 is to 18 as what is to 6? It's a third, so it should be 1. So that should be 1 kip per foot. So once I know that, I can find the concentrated equivalent for that section. 1/2 base times height, that's 3. So it's 3 kip force. What's the distance from the cut? 1/3 the distance. 1/3 of 6 is 2 feet. Everybody see that?
Do that again.
Say again?
I said do that again.
I can't hear you, I'm sorry.
I said do that again.
Do which part? Well, remember the equivalent force is the area under the curve. So it's a triangle, so the area of the triangle is 1/2 base times height. So 1 times 6 divided by 2, that's 3. And then the distance to the centroid is always 1/3 from the big end. And 1/3 of the distance, or 1/3 of 6, is 2. So now on this section, I'm going to assume positive axial force at C, positive shear force at C, and positive bending moment at C. So you can get lots of practice, hopefully, of putting these in their proper sign convention. Again, as far as I'm concerned, the problem's really more than half done. Because now you can just get out your statics monkey and grind the wheel. Don't literally get out your statics monkey. That would be a disaster. But mentally. So I've got my statics monkey on. So I'm going to sum moments about the cut equal to 0. Now what kind of moment is that with my sign convention? Positive. What kind of moment does the 3-kip force create about the cut? Positive. So the moment would be force, 3 kips, times distance, 2 feet. The only other force I have is this 9-kip force. What kind of moment does it create? Negative. So I got force, 9 kips, 6 foot distance. So it looks like the moment at C is positive 48. And that's kip feet. Does it make sense that this structure has a positive bending moment? Yeah, under this kind of load, you'd expect the beam to bend kind of like that. And that looks like a smile, so you expect it to be positive. So the last little bit we need to do is to sum forces in the y direction. Make sure we have equilibrium. So up being positive, this shear force is acting down. This load is acting down. This reaction is acting up. So it looks like the shear at C is equal to 6. So we have positive shear force at C equal to 6 kips. Any questions about that?
We're going to see that one.
You're not going to see that on the exam either. Baby steps, baby steps. We're just stretching. We're just stretching. We haven't gotten to the sprint yet. Any other questions?